Hey guys, welcome back. Today should be a little bit shorter than what we did yesterday, gratefully. We also are going to do a proof for the exterior angles of a polygon and kind of first revisit whether or not a circle is actually a polygon. So polygons have many angles. The poly and the gon means if we define a polygon as a closed geometric figure with three or more straight sides, then the question is, how do we view a circle? Does it have one curved side? Then it wouldn't be a polygon. Or does it have infinitely many sides that are all straight? So kind of looking into that again. So let's look at all the polygons that we have. So this one is a triangle, also known, I guess, as a trigon. Just kidding, it's really just triangle. Quadrigon, right? No, quadrilateral. Okay, see how we do on this one. Pentagon, hexagon, hepta or septagon, either way. Whether you want to do Greek, it's the hepta, or the septa is the Latin. And then octagon, everyone knows that one. Again, like October, as in what used to be the 8th month when we started the years out in March. And then nonagon, like November, I guess. Decagon, like December, my birth month. And then undecagon, you can just call it an 11gon if you want, though. You don't have to remember. I mean, all these have names, but we'll see if I can remember. Dodecagon, and then tridecagon. Yeah, tridecagon and tetradecagon. And then, I don't remember that one. Yeah, pentadecon. Should have been able to figure that one out. But anyway, you can just call them 11gon, 13gon, 14, and 15gon. And if you're not sure about any of them over 10, just do that anyway. And as you notice, as we increase the number of sides, eventually it starts to look just like a circle. So could a circle be a polygon with infinitely many sides? That's kind of how I choose to look at it. Here's a really cool visual. So here we start with a triangle and then a square. They all line these up here, which is kind of nice. And then we have a pentagon, then a hexagon, then a hectagon, then a nonagon, then decagon, I believe, at the end. Or I got off somewhere. But anyway, really cool visual. Kind of nice. Wish I had one of those. Here's a hectagon. And if you look at it, it's a 100-side figure, and it looks a heck of a ton of a lot like a circle. Anyway, see what I did there. Like an infinigon, right? So if we can imagine, even when we look at this one with 100 sides, you could really barely tell the difference between a hectagon and an infinigon. Interesting. Huh? You'll never know. All right, so here's our proof, pretty quick in here. Sum of the interior angles of a triangle, we know these three have to add up to 180 degrees, so that's not a problem. So the sum of the interior angles, which you can kind of write with a sigma of interior, is equal to 180 degrees, at least for a triangle. If not, we do the sum of the interior angles is equal to our formula, which is n minus 2 times 180 degrees. And if you remember, this n minus 2 was telling us the number of triangles that we have in the polygon if we start in one point, which is what we did yesterday. So if you haven't seen that part, I think it was number 22 in the problems, really make sure you go back to that. I guess we will reference it again today. Then what are the sum of the exterior angles of a triangle? Well, we looked at like the interior angles of like an equilateral triangle, and if all of those were, say, 60 degrees, then that means all the exterior angles, their supplements, would be 120 degrees. So 120, 120, and 120. And we add that together, we ended up with the sum of the exterior angles, at least for a triangle, was equal to 360 degrees. Which is pretty cool, and that actually works for all triangles. So let's see what happens. Let's see if we can prove that real quick. So here we have a triangle with 3 interior angles and 3 exterior angles labeled here. And so we have also, so these 3 interior angles, so we got 3 of these eyes, and then 3 of these exterior angles as well. And those together, the interior and exterior angles, add up to 180 degrees. So that is going to add up to 3 linear pairs, which is going to be 3 180 degrees. So if you see that, the green and the blue, and the green and blue, the green and blue add up to one of these 180 degrees because they are supplements, they're linear pairs, right? So the 3 interior plus 3 exterior is equal to 3 times 180 degrees. Well, the 3 interior angles we know is 180 degrees, so that means that the 3 exterior angles has to be 3 times 180, which is 540, and then all we do is subtract the 180 from both sides. Let me see if I write that in real quick. So minus 180 minus 180, which is going to leave us with the 3 exterior angles has to be equal to 360 degrees. So we can prove for any triangle, because we know the 3 interior angles have to add up to 180 degrees. For any triangle, the 3 exterior angles has to add up to 360 degrees, because there are 3 linear pairs in there, so the sum of those two has to add up to 540, and therefore the 3 exterior angles have to be 360 degrees. So we just proved that from what we knew about interior angles of a triangle adding up to 180 degrees. All right, so what about a quadrilateral? So quadrilateral has four sides. It's a very similar proof. So we have four interior angles, four exterior angles, and each one of those pairs are going to add up to a linear pair. So we're going to have four linear pairs of 180. So the 4 interior plus the 4 exterior is going to be equal to 4 times 180. 4 times 180, by the way, is 720. So we also know the 4 interior angles from our formula is going to be n minus 2 times 180, which is the number of sides of 4 minus 2, which is 2 triangles, right? If I split a line across here, we'd have 2 triangles. And 2 times 180 for each triangle would be 360 degrees. So 360 degrees plus the 4 exterior angles has to be equal to 720. Then we just subtract the 360 from both sides, which leaves us with the 4 exterior angles have to add up to still 360 degrees. So that's interesting because it was 360 degrees for the triangle. Now it's 360 degrees for the quadrilateral. So what do you think it is for the pentagon? Believe it or not, it's actually still 360 degrees. So for all polygons, regardless of what they are, the number of sides, their exterior angles are always going to add up to 360 degrees. So we can actually prove that with some generic n-gon, which has n sides. So I know this one technically has 1, 2, 3, 4, 5, 6, 7. So this is a septagon. But technically just pretend like it was an n-gon, which can have any number n sides, whether it's 3 all the way up to an infinigon, technically. So the n interior angles plus n exterior angles is going to be equal to the n linear pairs. So just like we had on the other two. So our n interior angles is going to be our formula, right? N minus 2 times 180 degrees. Right? N exterior angles is what we're trying to prove for or solve for, so we're going to leave that alone. Then n times 180 is going to be 180n. Then next thing I have to do is actually distribute the 180 through to the -2 and to the n. So when I do that, I'm going to get 180n minus 360. Now this 360 is actually where the exterior angles come from. That's the whole point. So whenever we distribute it through, it's not just n times 180, it's n times 180 minus 360, which is why the exterior angles are always going to add up to 360. But we'll finish the proof out so that you can see it. So 180n minus 360 plus the n exterior angle is going to be equal to 180n. Then we want to solve for this. So we need to move all this stuff to the other side. So what I'm going to do is I'm going to subtract 180n from both sides and then add 360 to both sides. When I do that, of course, these are going to add up to 0, and these also add up to 0, leaving with just 360. So what I'm left with is n exterior angles is going to add up to 360 degrees. So regardless of what n is equal to, regardless of how many sides we have or how many linear pairs, it's always they're going to cancel out, and the n exterior angles are always going to be equal to 360. Now where that 360 came from, again, it's this part right here from the n minus 2 times 180. Now I've got another proof that actually involves the triangles going to the center of the polygon, but I'll show you that probably tomorrow because I don't want to do too much and overwhelm you in one day. All right, so that's it. Pretty short lecture, going right into the assignment at this point. So on number 1, we have a quadrilateral. It's got 4 sides. So we want to find the sum of the interior angles. So we're going to use our formula. And the formula is n minus 2, which is a number of sides minus 2 times 180. Now this n minus 2 tells us how many triangles we have, which we discovered that pattern yesterday is always 2 less than the number of sides. So for instance, when we have 4 sides on a quadrilateral, that means if we create a diagonal here, we're only going to have 2 triangles. So n minus 2, 4 minus 2 is 2. So there are 2 triangles, and each one of those triangles is going to have interior angles that add up to 180 degrees. So the triangle on the top, these 3 angles are going to add up to 180, and the triangle on the bottom, all 3 of these are going to add up to 180 as well. So altogether, the sum of the interior angles is going to be 2 times 180, which is 2 times 180, which is 360 degrees. Okay, then we have our octagon here, which is like a stop sign. We're going to plug it into the formula, n minus 2, so 8 minus 2, which is going to be 6 times 180. So it has 6 triangles, and we can even see that here. So there's 1, 2, 3, 4, 5, 6. Kind of cool. So 6 times 180, and we're just going to plug that into our calculator. You're probably going to have to use your phone if you don't have a calculator at home, which is just fine. All right, which is going to be 1080. So 1080, no problem. Now you'll notice on number 10 and 12, those problems are exactly the same as the first one. So we've already found that the sum of the interior angles from number 1 is for a quadrilateral is 360 degrees. Now they want us to find if it's a regular polygon, what is the measurement of one of the interior angles? Well, that's actually pretty simple to do. So if all of the angles, and there would technically be 4 of them, right? So if those 4 angles, or those 4x, all have to add up to 360 degrees, then how are we going to find out what one of those x's are equal to? Well, just simply divide 360 degrees by 4, which will leave us with x is equal to 90 degrees. And sure enough, of course, in a square, the one interior angle is going to be 90 degrees. So a similar thing happening down here with our octagon. Again, remember there would technically be 8 of these angles, and because it's a regular octagon, they're all the same value of x, which will be different on the next problem we do, by the way. So whenever we would do this, basically we're going to have 8x is equal to 1080, because they all add up to 1080, and all we have to do is divide it by 8, which is going to leave us with x is equal to, I don't know, let me put it in the calculator. So you have 1080 divided by 8, which is 135. So each one of these angles has to be equal to 135 degrees. Let's see if I can do that. Okay, yeah, 135 degrees. Very good. And you'll just finish that pattern from the first 9 into the next problems, the next 9 problems as well. So, all right, on number 21. So on this one, we have a pentagon. It does have 5 sides, but if you notice, it's not a regular pentagon. All the angles are different, all right? So we need to find out what one of the angles are going to be. Well, I think it's 108 degrees if they were all the same, but it's not regular, so it's not 108. But what we want to do is we want to go ahead and actually add them all up and then set it equal to the sum of the interior angles for the pentagon. Now our formula still holds true even if it's not a regular quadrilateral or a regular pentagon. So we have 5 sides, so 5 minus 2 is going to be 3. 3 times 180 is 540 degrees. So all together these are going to add up to 540 degrees. So when we add them together, I'm just going to put it in the calculator. So 124 plus 118 plus 100 plus 100. It's going to be 442. So this 1x plus the 442, and all I did was combine those like terms, is all going to add up to 540. Then to solve for the missing value of x, we're going to subtract 442 from both sides, which is going to leave us with, I don't know, I'll do it here. So 540 minus 442, which is 98. So the missing angle x has to be equal to 98. Now, in your kind of answer bank over here, it's going to guide you through the problem. So the first thing you need to do is name the polygon. It's got 5 sides, so it's a pentagon. Then find the sum of the interior angles, which we did up here. So 5, the number of sides minus 2 is 3. 3 times 180 was 540. And then the x, that was whenever we set up our equation, x would have had to have been equal to 98. So that was the missing angle that we had there. All right, then the rest of the assignment is actually pretty cool because we get to talk about coins, and so you got some eye candy to look at here. So there are a lot of actually, there are a lot of coins that are in the shapes of polygons, which is kind of fun. And so I got to research some of those, and there's some captions on there that'll actually tell you where they come from. So this is a 50-pence piece here. It's in the shape of a regular polygon. Name the regular polygon, then find the sum of the interior and exterior angles, and then the measurement of the angles labeled 1 and 2. So 1 is going to be one of the interior angles, and 2 is going to be one of the exterior angles. And we can actually find those angles because this is, in fact, a regular polygon. So first thing we'll do is name it. So I guess I'm going to start at the top. So we got 1, 2, 3, 4, 5, 6, 7 sides, which would make it a hepta or a septagon, whichever one you want to call it. It's just fine. So to find the sum of the interior angles, we've got 7 sides. So we have 5 triangles. So 5 times 180. Which is going to be 900. So the sum of the interior angles is going to be 900. The sum of the exterior angles, if you remember what we proved today, is the exterior angles always add up to 360 degrees. And that comes from the n minus 2 part in our formula. And then, so what is one of the interior angles going to be? This one here. Well, if you remember, there's going to be 7 of them all together, and they have to add up to 900. So all we're going to do is 900 divided by 7, which is going to tell you what each one of them has to be. We're going to round to 1 decimal place. I think that's what's on the answer bank. So 128.6 degrees. And then to find what one of the exterior angles are going to be, we know the exterior angles have to add up to 360, right? Okay, so, and there's 7 of them. So 360 divided by 7, which is going to give us 51.4. You'll also notice the relationship between these two. So this one actually could have been moved up there. And these two, of course, have to be a linear pair, right? They have to add up to 180 degrees. So if we know one of the interior angles has to be 128.6, that means that the leftover exterior angle is going to be the supplement of it. So 180 minus 128.6, which would give us the 51.4 0.43. So you can actually use the fact that we know the exterior angles has to be add up to 360 and then a number of sides to work backwards. And once you have what the exterior angle is, you know what the interior angles are going to be. Then if you multiply that by the number of sides we had, you could find out what the sum of the interiors. So it's actually kind of cool. You can work both ways. And I'll actually demonstrate that on this one if it doesn't confuse you. All right, so I'm going to start, I guess, at the top. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it's 11 sides. You can either call it an 11gon or an undecagon. I guess I just call it 11gon. And so if there's 11 sides, and we know the exterior angles, of course, have to add up to 360. That's true for all of them. So what is one of those exterior angles going to be? So I'm going to do 360 divided by 11, which is going to give me 32.7. So one of these exterior angles, which would be the 32. Keep in mind, this one's technically an interior angle, right? Because it's vertical with the interior. I just put it on the outside because it wouldn't show up very well if I put it on the inside. So that one angle 2, the exterior angle is going to be 32.7 degrees. And if that's the exterior angle, I can subtract it from 180 to find out what one of the interior angles are going to be. So I'm going to do that real quick. So 180, and I'll do minus the previous answer. So second ANS. All right. Which is going to mean that one of the interior angles, angle 1, is going to have to be 147.3 degrees. And sure enough, it is. Now, we could have found that the traditional way by using our formula. So how many triangles? If we have 11 sides, that's n minus 2. 11 minus 2 is 9. So 9 times 180. That's going to be the sum of the interior angles, which is 1620. And then if I divide that by 11, because there's 11 interior angles altogether, we get the exact same number. So kind of cool. You can use what you know about the exterior angles. It might even be easier for you. Or you can use the formula and work forward instead of going backwards. All right, it's kind of cool. I think this one's a French coin, and it's an octagon. It looks just like a stop sign, doesn't it? So it's an octagon. Some of the interior angles, so we have 8 sides. 8 minus 2 is going to be 6, so we have 6 times 180, which is 1080. For all the interior angles, there's 8 of them, so I'm going to divide it by 8, figure out what each one of them, okay, each one of them is going to be 135 degrees. So if that's the interior angle, the exterior angle is going to be the supplement of that, which is 45 degrees, right? So if I write that here, the interior angle is going to be 135 degrees. This means, let's try that again, but I'm going to lift my pen. I said I was going to lift my pen. There we go. Then the exterior angle is going to be the supplement of that, which is 45 degrees. All right, number 30. It's actually an Australian coin commemorating the soldiers who fought to free Passchendaele, which is a city in Belgium, I think, from World War I. See how many sides we have. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is a dodecagon. Some of the interior angles is going to be 10 times 180, which is 1800. That one's kind of easy because you're just multiplying by 10. Then we're going to do 1800 divided by 12 to find out what each one of the interior angles are going to be. So 150. And that's pretty easy because if the interior angle is 150, that means the exterior angle is going to be simply 30. We'd also figure that out by doing, of course, the sum of the exterior angles of 360 divided by 12, which should be 30, and it is. Very good. I'm not sure if that's the last one. Nope, we got Tuvalu. Tuvalu is a small island in the South Pacific. So not surprisingly, they've got a sea turtle on their coin, their $1 coin. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is a nonagon. It's kind of cool. The interior angles are going to add up to 9 minus 2, which is 7. So 7 times 180, which is 1260. Alrighty. And then we divide that by the number of angles, which we said was 9 because it's nonagon, which would be 140 degrees. We know the exterior angles, as always, for all polygons is going to be 360. And we could do 360 divided by that, or you can just find the supplement of 40, which is, of course, going to be 40 as well. So if I did it the other way, so 360 divided by 9, which would give us 40, of course. All right, so that's it. This is just a review here. In case you're curious, you can freeze the screen. It's what I normally do in class. And here's a bunch of cool coins and all their awesomeness. I wish I had polygonal shaped coins. That'd be really cool. All right, well, we're under 20 minutes. I hope you guys enjoyed that. We will have a review of these for you to do tomorrow. So this lesson will be done live on Friday if you're a B student, but if you're an A student, because we only met yesterday on Tuesday, then you'll have to do this one on your own. But it's all pretty easy and it shouldn't be that big of a deal. But let me know if you have any questions, and I'd love to help. See you guys.